So thank you again for joining us, and let's go ahead and get started here. Just basically, this is our agenda. These are some of the high points that we hope to cover today in the webinar. Obviously, I'll do a little introduction myself, go over Kitagawa North Tech, who we are, our ownership, and then we'll get into some chuck types, talk a lot about wedge style chucks, which are really your standard chuck. It's the chuck that comes on basically every CNC lathe built around the world has a wedge style open center power chuck on it. Talk a little bit about how chucks and cylinders work together, cylinder pressures, grip force loss, and then get into some typical causes, I think, for grip force loss. I think that people have had experiences with parts coming out of chucks and maybe wonder why. We'll talk a little bit about that, and hopefully, hopefully cover quite a few topics that folks that that use chucks or that maybe sell machines with chucks on them have heard from their customers, issues pertaining to chucks. Hopefully we can cover those, and again, I assume there'll be some questions at the end, and we'll get through those as well. So just a brief overview of who I am. Basically, I started here at Kitagawa in 1994, right out of college, and have really been in work holding my whole career. For the most part, here at Kitagawa, roughly 21 years here at Kitagawa North Tech. A few years outside of the organization, but also in work holding. And really, this is, again, coming out of college, this is really all I know and really been my my life's work. So hopefully what I share with you is will be of interest, and maybe hopefully some folks will learn some things from it. So kicking it off, just a brief history and background of Kitagawa North Tech. So the Kitagawa Corporation, which is our one of our parent companies in Japan, has been around over 100 years. I think, the Kitagawa brand has been synonymous with standard chucks for a long time. We've been coming in on machines manufactured in Japan for a very long time. We've supplied domestic organizations with domestic production as well. But we've really been synonymous with the standard chuck, standard cylinder on most machine tools. Here in the U.S., we've actually been in the U.S. Since the late 70s, opening our first office in New York, and then quickly moving here to the Chicago area, where we established our headquarters, this particular location, in 1991. We do all of our North American operations out of this building. It's roughly 40,000 square feet. Carry all of our inventory here, manufacturing here. Inspection, testing, sales, marketing, engineering, everything is done here. So we are, this really serves as our main jumping off point, and we hope when this pandemic is over and we can all get back to some sense of normalcy, we really like to invite customers in to see what we do here and give them firsthand, hands-on experience with our products. Our parent companies, our ownership, we are owned by, in part, both Nippon Steel, Nippon Steel, probably better known for the steel coils and its trading company business. But Nippon Steel is a very large company, roughly 24 billion in annual sales, almost 8,000 employees worldwide. And we're a part of their industrial supply and infrastructure division. In addition, we were also partially owned by Kitagawa Corporation in Japan. So obviously our namesake, but the Kitagawa Corporation is a separate company, and they manufacture the majority of our products that we sell and distribute here in North America. And Kitagawa is roughly $530 million company with just under 1,400 employees, primarily in Japan, but a few stationed in other parts of the globe. So let's we'll get into the meat and potatoes of it now. Really, we're going to kind of get again, going back to the agenda. We're going to focus on some of the major points, some of the major issues with power chucks and chuck packages, and maybe some of the things that again users see on a pretty regular basis, and some of the problems they have, and maybe how to solve them, or at least give you some new thoughts on it that you might be able to deploy in your own shop. Some of those things: maintenance, grip force loss. What causes grip force loss? Why do chucks open up? Why do they throw parts out? Why do parts move in the cut? What can contribute to that? And then lastly, we'll talk a little bit about some of the other issues with chucks: jaw forming, jaw lift, how to improve that. What are the common causes of repeatability issues, particularly when you take jaws off and put them back on. So again, hopefully we'll cover some topics that you guys are interested in, and we'll generate some questions at the end. So when we think about power chucks, there's really, there's more styles than just this. But when we think about your chuck that you would most commonly find on a CNC lathe that you might buy new, you're gonna come across lever style chucks and wedge style chucks. And like I said before, wedge style chucks are really the OEM standard. That they're what you are going to find from machines built in Korea, Japan, Taiwan, anywhere in Europe, really anywhere around the world. Your standard lathe with an open center chuck package is going to have a wedge style chuck. Lever style chucks are traditionally used when you have a jaw stroke. Special jaw stroke requirement. They're really geared around long stroke applications where you need to have an excessive amount of jaw stroke. As we look at lever style chucks, kind of in contrast to wedge style, a lever style chuck has a mechanism internally that pivots around a center point. It engages the master jaw. So as the draw tube, or as when you hit the foot pedal and the draw tube pulls back, the hydraulic cylinder pulls back in the Z-axis, it actuates a lever, a rocking motion in this lever, and then the master jaw then clamps, moves in towards the center in a radial direction. This mechanism provides a long throw. It provides quite a bit of movement to the master jaw, which gives you that jaw stroke that you need for certain applications. The only real downside to lever style chucks is they tend to be inefficient at making grip force. So as you apply drawbar pull force or draw tube pull force to the inner plunger system, as that pulls back, the mechanical advantage that you get out of the lever tends to be weaker or less than a wedge style chuck. So while you might select this for, again, a jaw stroke application, something that you need to open the chuck jaws, swallow a flange, and then grip down on a smaller diameter just beyond that, you're not going to produce the kind of grip force that you might need for high speed aggressive cutting. The other thing sometimes you see with lever style chucks is the through hole. The actual available through hole in the chuck gets smaller. Again, because the body, the available room in the body to put all of this mechanics tends to lessen that through hole size. It's not 100% true, but for the most part, when you look at a lever style chuck, and particularly when you try to replace a wedge style with a lever style, you have to be conscious of the fact that the draw tube might be larger than the chuck can handle. Moving on to the most common chuck that is found on your CNC lathes as you buy new equipment, really over the last probably 35, 40 years. Most of them are open center. Most of them are wedge style. The wedge style chuck is really a general purpose, all-purpose rotating vise. It's designed to clamp a variety of parts. Folks that are in a job shop environment, all the way through to folks that might be in a tool room in a 1,500 or 2,000 employee production tier 1 automotive company. But these are, these chucks have been around a long, long time. They're very, very robust. They do provide a very efficient way of converting linear, your z-axis linear motion, your draw tube motion, converting that into radial gripping motion. In contrast, when we talked about lever style chucks will take roughly 1 pound of drawbar pull force in a lever style chuck will produce about 1.5 pounds of grip force, total grip force. A wedge style chuck, 1 pound of drawbar pull force equates to 2.5 pounds, roughly, give or take, 2.5 pounds of grip force. So the wedge style chuck is an extremely efficient way of converting your z-axis movement from the draw tube and the hydraulic cylinder and converting that into gripping force. Again, these are, these chucks tend to also allow for a larger through hole. So you'll find a lot of the late model CNC lathes available today on the market have a large through hole relative to the body diameter of the chuck. So 15, 20 years ago, Kitagawa's standard chuck was we'll say an 8-inch chuck. The standard chuck was a B208. A B208 had a 52 millimeter through hole, allowed you to pass a 2-inch piece of bar through it. Very quickly, consumers said, hey, we want to do a little bit more with the same footprint. So very quickly, we developed the BB, the big bore series, and the BB208, which replaced the B208, now provided 66 millimeters of through hole. So now you had still an 8-inch chuck body diameter with 2.5-inch bar capacity. So the wedge style, again, very, very efficient making grip force, very robust, and does allow for an exceptionally large through hole compared to the body diameter of the chuck. As we look at power chucks, as we get into some of the later information here, as we get into some of the issues pertaining to grip force loss and some of the variables that affect that, I'm showing this slide really just to kind of point out that if you are in and around chucks, most chuck manufacturers, regardless of who they are, have some specifications available on their website or in a catalog. The red items here that are boxed up, these are some of the key variables that we look at when trying to determine if a chuck is performing correctly and calculating cylinder pressures and that kind of thing. The first one to look at is maximum drawbar pull force equating to maximum grip force. And again, going back to the 1 pound to 2.5 pounds, you can see 22 kilonewton of pull force equates to 57 kilonewtons of grip force. So there's your ratio, for that 2.5 to 1 pull force to grip force in a wedge style power chuck. We also look at plunger stroke. We want to make sure that we understand how much z-axis movement it takes in the chuck body to create the full jaw stroke of the chuck. And the reason we might want to look at that is if you notice that you aren't getting full jaw stroke, you do want to make sure if you're not getting 5.5 millimeters of diametrical jaw stroke on your B206 chuck, you want to make sure that you're getting the full 12 millimeters of plunger movement on the chuck body first. Also, we, along with most manufacturers, will provide a matching cylinder, some information on matching cylinder, not even see a maximum operating pressure for that cylinder and that chuck. So when those two devices are coupled together, there is a maximum cylinder operating pressure that we do not want you to exceed. And then lastly, soft jaw information, and this will become more important later again as we talk about grip force loss. But we identify what the standard Kitagawa power chuck comes with in terms of the soft jaw. Because there's so many aftermarket jaws available out there that we want you to understand how those dynamically or how those affect grip force in a rotating chuck. The same is true for the hydraulic cylinders. So I just show again a specification table pulled from a catalog for a Kitagawa SS cylinder. But what we're looking at is really once we define what cylinders on the back of the machine, and most machines, most late model CNC lathes they have a placard, a plate on the side of the machine that indicates what chuck and cylinder are on the machine. There's usually a list of them, and there may be a little dimple. They might have put a little dimple next to the one that is on your particular machine. As long as those two devices remain on the machine, the cylinder pressure that they show on the placard is accurate. You have to make sure though that if you change the chuck, if you put a collet chuck on in place of the wedge chuck, or you put a quick jaw change chuck on in place of the wedge chuck, those values are now null and void. They are not accurate any longer, and you have to recalculate your maximum allowable drawbar pull force for that cylinder and that new chuck. Here, 1 second. I just want to make sure we have everybody on board. Okay. These are key values. The plunger stroke shown here, 22 millimeters of plunger stroke. As we saw in the chuck specification, the chuck required 12 millimeters of stroke, Z-axis stroke. The cylinder clearly produces that much or more. And then we look at pull side on the drawbar pull force of the cylinder. Again, it produces more pull force than the chuck requires, so we're safe there. And then just again, as we do some calculations later, this is the max operating pressure is just discussing the independent maximum pressure for this cylinder, not what the max pressure is for this cylinder and chuck, but what the not to exceed pressure is for this cylinder by itself. So if you were to take an OEM chuck off of the machine spindle and put a larger chuck on, you upsize, or you put a quick change chuck on, which requires more pull force, this cylinder has a significant amount of available pull force, much more than what is traditionally used in a standard chuck package. So when a machine tool builder supplies you a machine with a chuck and cylinder package, generally the cylinder is sized in a manner that is much larger, much more powerful than the chuck, because it gives you that flexibility to either upsize the chuck or put something else on in place of the wedge chuck. But it also allows you to operate the cylinder in a pressure range well below its maximum. So that way you're not operating the cylinder at high pressures, high speed, and heating the cylinder up, eventually jeopardizing the bearings and some of the other internal parts. As we put those two things together, this drawing just really here is to indicate a standard, more traditional chuck package. It shows the hydraulic cylinder on the back of the lathe. What you don't see here is the headstock of the machine. So this is like if you took a section view down the center of a typical, CNC lathe spindle cartridge. You're going to see, the hydraulic cylinder mounted to the back, the power chuck mounted to the front, and then the all-important draw tube that actually connects the two devices. So, when you look at your standard lathe, what you can't see just looking at it, you can see the cylinder usually behind some protective sheet metal enclosure, and you see the chuck. But what you don't see is right down the middle of the machine through the spindle bore is a tube, and that tube is very, very important. Its design is very important. Its wall thickness is very, very important. A lot of people want to maximize the through hole available through their chuck package, but to do so, you have to be very, very careful that you have enough tensile, yield, fatigue, that you have enough strength in that tube to accommodate that. So just kind of pointing it out, you have your chuck, your cylinder, your draw tube, and then at least when you're working with us, we'll provide an assembly drawing of this system, and then generally you're going to get a specification table in the drawing. One of the things you'll get, which is maybe difficult to see depending on the size of your screen, but the very last thing here says maximum pressure for this particular cylinder and this particular chuck. So that we provide the user with a maximum operating pressure for this chuck and cylinder package, using, the key thing here is using the standard Kitagawa soft jaws that come with the chuck. We'll talk again a little bit more about how the jaws affect grip force and grip force loss, but every calculation, or I'm sorry, every specification you see either on a machine tool placard or in a catalog, or any specifications you see from any chuck builder, any chuck manufacturer, they're based on their soft jaws. They're based on the standard soft jaw height, width, and length, or mass. And if you take those off and you change it and you put pie jaws or any other type of jaw on there, you are changing those specifications. What affects grip force? And grip force is really, you know, it's I think the thing that is near and dear to everybody's heart. If you're standing next to a machine and that chuck's spinning at 2,000 or 3,000 RPM and you got a part in there, you know, maybe, you know, nowadays the doors are pretty well reinforced and you're pretty safe standing there. But I'm sure everybody that's been in manufacturing for any length of time have heard horror stories about parts coming out, hitting doors. You know, we as chuck builders, we've gotten calls like that over the years, and definitely have had to go through and diagnose why it happened. So grip force is critically important. You always heard the phrase "speed kills" when we're talking about driving cars. At excessive speeds, the same thing happens with chucks. You spin that chuck super fast, put great big tall jaws on there, get some aggressive cutting conditions going, and that part's going to want to come out of the chuck. So we'll talk about the chuck condition, how that affects it, lubrication, a big critical key point. You've all heard us talk about greasing your chucks, how speed affects it, how jaw height affects it, and mass affects it. Big thing here is the periodic disassembly of your chucks, and you know while it's important to grease your chucks, we have to understand that wedge style power chucks, again the ones that are found on all your lathes, they have very tight fits and tolerances between the sliding surfaces. So if you do not continuously lubricate your chuck with the proper grease and you let it go for a while, it's very likely that the internal components and the internal fits get clogged up. I mean, literally the grease itself will begin to degrade, coolant and other swarf will migrate into the chuck, and some of these greases will become, you know, like a solid. I mean, they'll become, basically they'll create a whole nother level of friction inside that body where the chuck will begin to lose its grip force. It'll begin to wear. You'll literally grind the grease in the sliding surfaces, causing additional gaps in the original equipment fits. Chuck it'll prematurely wear out. But the other thing you have to consider is that the grease fittings, they're little tiny fittings that are in the master jaws. If you don't grease it regularly, those will become clogged up. And when you go to put new grease in the chuck, you pump away, you put the grease in there, you think you're getting it into the sliding surfaces, and it never even makes it into the chuck. You grease it, you put the grease gun away, you fire it up, you spin the chuck, and then it leaves a nice gray or whatever color ring around the inside of your machine, and you don't even get the grease to where it needs to go. So the disassembly of the chuck is partially to make sure that all of the labyrinths, the greasing labyrinths, are cleaned out, the fittings are cleaned out, and that you can actually get the grease to the places you want to get it to. Obviously, probably one of the most critical things is greasing and really the selection of grease and how we go about the frequency of greasing. So many people over the years have really gone to readily available grease that might be at your local auto parts store, or something called a high pressure grease, or maybe use lithium greases. There's so much information out there, misinformation, frankly, that people have gotten over the years, and not all grease is created equal. So, of course, we offer grease, and we have brands that we've created and that we would like to see you use. But really, what you're looking for is a grease, typically a molybdenum-based grease as opposed to a lithium-based grease, and a grease that the formulations that we've tried to come up with are tacky, so they really try to keep the grease inside the body rather than slinging it around the inside of the machine. Of course, we'd like to see you grease the chucks once a day, once a shift. Again, keeping keeping the labyrinths open, keeping the grease flowing and moving through the chuck properly. So the two grease products that we talk about and really promote is our Tri-Coat, which we actually produce here at Kitagawa North Tech in the U.S. But also the Chuck Grease Pro, which is the grease that's formulated in Japan and is what is sold and recommended by Kitagawa Corporation. Both of them, again, are really kind of equals, and they do provide a similar result. What does the grease do? If you were to disassemble your chuck, take the wedge plunger out, the master jaws out, and put them under a microscope, they're basically steel surfaces. Yeah, things have been ground, but microscopically, there's still peaks and valleys. There's highs and low spots, and if you don't lubricate the chuck with the right grease, those little peaks begin to break off. They essentially rub together. They break off. They now contribute to the swarf that's inside the chuck. They contribute to things binding up. They contribute to getting to the greasing labyrinth that runs down the tongue of the master jaw, and just creates friction. And friction equals performance reduction, equals grip force loss. So the lubricant, the grease, really fills those voids, creates almost like a hydraulic barrier between the two surfaces, allowing them to slide very efficiently across each other, and will produce better grip force at speed, and really prolong the life expectancy of your chuck. An example of this, and this is taken with a dynamic jaw force analyzer, but an example of this is just one of our power chucks, wedge style power chuck, where we used a lithium grease. We took an aftermarket grease, lubricated the chuck, clamped on the jaw force analyzer, tested the grip force at 1,000, 2,000, 3,000, 4,000, and 5,000 RPM, and we plotted the grip force loss curve. So we started at 8.7 kilonewton of grip force and degraded to 3.4 at 5,000 RPM. By contrast, we take the chuck apart, completely remove all the lithium grease, grease it then with our tri-coat grease, and we see a significant performance improvement just by changing the grease, just by creating that barrier between the two, the sliding surfaces. The chuck becomes much more efficient at making grip force at the same cylinder pressure and at the same speed. So, you could imagine that if you're having issues with parts coming out or slipping, or you're just getting, you just have a really aggressive cut, or maybe you just have it's a second operation. You're gripping with a smooth set of jaws on a smooth gripping surface. You just don't have a lot of friction there. So the part is going to more easily try to move in the cut or spin or come out. You want to make sure you've taken care of that chuck. You want to make sure you've greased it, that you're giving yourself the best chance of holding on to that thing at speed. Again, the big thing here too is power chucks, as we've gone along, have gotten more and more expensive. Your average 8-inch chuck might be $3,000 or so, $3,500. And if you get into some of the bigger ones, you can spend 10, 12, 15, sometimes 20 grand for a power chuck. A tube of grease is pretty inexpensive. It's an insurance policy to make sure that thing lasts as long as possible. It's also a safety feature because, you just don't want to jeopardize grip force. Basically, this screen here, what we're talking about this diagnostic tool to measure grip force and grip force loss. This is a dynamic jaw force analyzer. This device, you would form a set of soft jaws, put this device in the jaws, grip on it, and it will output to your laptop or to this handheld device how much grip force you're getting, total grip force you're getting in your power chuck. But we use this mostly as a diagnostic tool in checking to see if a chuck is performing as we expect it to. Typically with these, you're not necessarily able to use it to grip using custom jaws or serrated jaws or jaws with grippers and things like that in it, because of course you would damage the load cells on the device. So we use it as a way to confirm that the chuck is performing as expected. This is a device. We do have a couple of these available for rent or for kind of in our fleet to share with you, for you to use to test your chuck performance. But generally, we like to use it. If we're able to come in and actually take a measurement with you, show you what's the different variables at play, because they can be a little bit confusing to use. And if you don't do it just right on how you center it up on your jaws, how you form the jaws to grip the load cell, you don't get the right readings, and then you might think you have a false negative. And so we would prefer to support you in this effort. Looking at, again, some of the major variables in grip force loss, speed is obviously a major factor, centrifugal force. And this plays a big role in, as we change our top tooling, as we change jaws, speed affects bigger jaws more dramatically, of course, than the standard jaws that come with the chuck. But this table, this grip force loss table, is available in every chuck manual that we provide with our chucks. They're also, for the most part, available on every manufacturer's website. They're available on when you go to the chuck page and you look up a specific, B200 series chuck, you'll see a chart like this that gives you the grip force up to one side and then speed along the x-axis. So you get the y-axis will give you your grip force, and the x-axis gives you the speed. So clearly, as you can see, one, as the chucks get bigger, 6-inch, 8-inch, 10-inch, 12-inch, grip force starts very, very strong, but drops off very, very dramatically. And it's really because the jaws get bigger. But you can see that as you speed up, as speed increases, grip force drops dramatically. So it's something to be conscious of. But again, this chart, like every other chuck manufacturer's chart, this is based on our soft jaws. This is based on the jaws that come on the lathe with the machine or out of the box. If you buy a new chuck from us, it comes with a set of soft jaws. All of this data, everything you see, max grip force, max speed, max allowable drawbar pull force, everything related to that chuck. And by the way, it's stamped. It's actually machined in the face of the power chuck. So if you lose all of your written materials or printed materials, right on the front of the chuck, we machine into the body, into the face, or some of the new chucks on the periphery, we machine into it the specifications for that particular chuck. But all of those specs are standard soft jaws. If you put hard jaws on the chuck, if you put pie jaws, if you put 6-inch tall soft jaws on there, all of that information is no longer valid. So segueing into jaws, and particularly jaw height and jaw mass versus grip force. I think, again, if you've been around machining for any length of time, if you sell machines, if you sell chucks, if you are an end user and you use chucks, you've all seen chucks, manual, power, otherwise, with extra large jaws on it. People try to take for example, a 10-inch chuck, and they want to grip a 12-inch part. Well, how do you do that? You put extended jaws on it, and you let them overhang the body, and you grip the part. Well, you can do it, it's possible, but you got to be very, very conscious of the fact that your grip force loss is now dramatically increased. The stress that you're putting on the T-nuts and the master jaws and the internal components of the chuck has just been amplified. Whatever hydraulic cylinder pressure you have previously set your machine to is also probably incorrect. You're putting too much force on the chuck. We've also seen very tall jaws. Jaw height is a significant issue that we deal with. As we look at some of these factors, again, in the owner's manuals of the chucks and also available on our website and others' website, we get into a discussion about jaw height and how it affects grip force and grip force loss. Main thing here, without getting too technical, we have a pretty diverse audience, so without getting technical and doing any kind of calculations, the thing you got to understand is that as the distance from the face of the chuck to the center of gripping height increases, center of gripping height, not the center of the jaw, but the center of the gripping height increases, your grip force decreases right out of the gate at 0 RPM. And as soon as you start putting speed into it as a factor in centrifugal force, it drops off rapidly. So when we talk about this H dimension, which again is from the face of the chuck out to the center of gripping height, right? Your gripping length is the actual length of the jaw that's gripping the part. We'll just say as an example, if your standard Kitagawa soft jaw has an H dimension, a center of grip height dimension of 37 millimeters. Let's call it 1.5 inches. So from the face of the chuck to the center of gripping height on your jaw, on the standard Kitagawa soft jaw, is 37 millimeters. You're going to be able to produce the values we show in our catalog for max RPM, max grip force, max allowable drawbar pull force. All of that would be okay. But as soon as you take those soft jaws off and you buy some aftermarket jaws that are, I'm just for math purposes, I'll just say, let's say they're 4 inches tall or 3 inches tall. So your jaws are 3 inches tall, and you bore into those jaws 2 inches. So you're not going to use the full length of the jaw, the full 3 inches. You're going to use 2 inches of that jaw length or height in the form of your gripping length. So you've got a jaw that's 3 inches tall. So from the face of your chuck to the top of the jaw is 3 inches, but you're boring into it 2 inches. That means your center of grip height from the face of the chuck to the center of your gripping length is 2.5 inches. So the original chuck, the standard jaw is 1.5 inches, but you've now increased it to 2.5 inches. You've added an inch in height, in H, in that center of grip height. By doing that, you've just now reduced that chuck's ability to produce grip force. So the max RPM that is machined into the face of the chuck, null and void, doesn't matter anymore, isn't correct. The specification shown in your catalog or shown on the website, incorrect. If the max RPM is 5,000 RPM with a standard jaw, you've just now knocked off probably 1,000 to 1,500 RPM out of that chuck's max RPM. So you now have a chuck on your machine that can only spin safely at 3,500 RPM. Again, as an example, kind of rough numbers here. The point to be taken is that the center of grip height dramatically affects your grip force and your ability to produce grip force. Some other factors to consider when considering grip force and grip force loss, gripping diameters affect the jaw dimensions, right? So if the gripping diameter is very, very small relative to a big chuck diameter, you might have great big jaws on there. You might have long jaws, extended jaws, but the jaw mass has increased. It's gone up compared to the standard OEM soft jaw. That can affect grip force loss. Coefficient of friction, this is maybe a technical term, but really you can imagine or intuitively a set of jaws with a knurled surface or teeth or carbide grippers, those penetrate the material. So those can grip into the material and actually penetrate it, giving you a high coefficient of friction between the jaw surface and the part surface. By contrast, if you are doing maybe a second operation, you now have a set of bored smooth jaws and a smooth, very, very, very clean, very smooth gripping diameter on your part. Those two things coming together produce a, very low coefficient of friction, which means if you've got a lot of cutting, depth of cut, feed rate, speed, you've got a lot of cutting torque, you're trying to spin that part, you're trying to rip it out of the chuck jaws, more likely to do it in that scenario than you are if you've got jaws that can bite into the part. Gripping force, again, going back to proper grease, going back to the jaw height, jaw mass, that grip force, that starting grip force at 0 RPM. When you grip that part, you want to know what that is. You want to know that you've got the full possible grip force for that application at 0 RPM, because as soon as you start spinning the chuck and centrifugal force acts upon the jaws, they're going to want to open up on you. So you want to make sure you've greased the chuck. You want to make sure that your jaws have the least mass possible, the least height possible for the application. Keep everything as close to the face of the chuck as possible. Otherwise, you run the risk of jaws opening up and parts coming out. Cutting conditions. Your cutting diameter relative to your grip diameter. When you're laying out an application, the more often you can make your gripping diameter larger than your cutting diameter, the better. Mechanical advantage. If your grip diameter is 6 inches and your cutting diameter is 3 inches, you stand a much better chance of holding onto that part than if you flipped it around and you've got a 3-inch grip diameter. Let's say it's now machined, so you got you got a smooth 3-inch grip diameter, but you're cutting on a 6-inch diameter, 6 inches away from the face of the chuck. So now you've got this, this cutting torque, this lever, this moment trying to rip the part out of the chuck jaws. So when you can flip when you're gripping on a smooth surface, in those instances, if that smooth surface, that grip diameter can be larger than the cutting diameter, you're better off. Same thing with depth of cut, feed rate, what we call cutting conditions. The more aggressive you are with those cutting conditions, depth, feed rate, and speed, the more cutting torque, the more force you're putting into the part trying to rip it out of the chuck. Those are variables you control as the user, and you may have to cut back on them in certain applications if the material may be difficult, or again, the only way you can hold it is a small grip diameter to a large cutting diameter. You got to consider that you might have to increase the cycle time in order to hold on to the part. The red items shown here are things that can be altered, obviously, and really grip diameter and those things could be potentially altered in the sense you could flip-flop operations to try to maximize your grip diameter. Jaw considerations, again, in speaking about grip force loss, we start thinking about jaw considerations because jaws are something that we change all the time. A lot of people buy aftermarket jaws. There's a dozen aftermarket jaw companies out in the U.S. market alone. You've probably all used them over the years, and there's some things to think about with that. One of the big issues that we found as a chuck manufacturer, as the original equipment company, is that the quality of some of the aftermarket jaws available out there to you is suspect. And by suspect, I'm talking about primarily the serrations. And in some cases, this is obviously, this is exaggerated, but what you need to consider is that if the serrations and if the jaws are not, we'll say flat, or the serration profile is inferior, you can risk prematurely wearing out your chuck, damaging your chuck, or maybe not the least of which is just repeatability and performance, gripping accuracy and repeatability of your chuck. But if you look at this, if you think about this, and again, it's exaggerated, but if the serrations, if the jaws are not flat, when you put the 2-socketed cap screws in here and you torque them down, you take as we know, very few people use torque wrenches when putting their jaws on their chucks, but you get a big Allen wrench and smack it around with a dead blow hammer. But when you torque those 2 bolts down, they draw the jaw down onto the master jaw, and when they do that, they cause the master jaw to twist. And if you look at any power chuck and you look at the end view of the master jaw, the cross-sectional width is fairly thin in some of the areas here where the T-nuts are engaged. So when you torque the bolts down, and if the jaws are poorly formed, once you torque them down, one of the 2 are going to try to give. One of them has to give way, and it's sometimes master jaw. And as the master twists, it's going to rub, because as you actuate the chuck, these sliding surfaces are going to rub together. And again, if you're not greasing it like you should, you're not using the right grease, you got some heavy grip forces, you put some inferior jaws on here, you torque the bolts down, you're going to put a lot of stress and deformation into the master jaws and into the body. That's going to cause the chuck to wear out prematurely. Also, it's going to cause you to have some, probably some poor gripping accuracy, some poor repeatability, and maybe even some grip force loss. When you buy an original equipment quality jaw from us, then we obviously stand behind it, and we produce what we believe to be a very good quality jaw that would minimize any of those types of issues. Another thing to consider with that is T-nut position. Again, if you've been around manufacturing any length of time, you might have seen people where the T-nuts which hold the jaws down into the master jaws. I've seen customers take the jaws and they push this out as far as possible, and the T-nuts actually come outside the master jaw. They're exposed. They literally push out and protrude outside the master jaw to maybe grip on a large diameter part, pushing the envelope of the chuck. But what happens is you've put the T-nut out of the master, and you've putting all of the grip force stress, all of the centrifugal force stress. You probably now have a big set of jaws putting a additional amount of lever moment and stress. It's all now being put on the T-nut, which is now not inside the master jaw. So it's not able to distribute that load over the full surface of the T-nut and master jaw. You're putting all of this extra force on a limited length of the T-nut, and what happens is, what we've seen is the T-nut combined with the top jaw, they literally pull off the top of the chuck. They rip off the top of the master jaw. They separate from the chuck at speed. So that the jaws, the part, everything comes out of the chuck. And it's a lot of times it's because of jaw height, it's because of jaw mass, it's because the T-nut is not fully enveloped in the master jaw. Another real common consideration, or maybe what people maybe don't realize or don't understand, is that the in pretty much every chuck, every sliding jaw chuck, right out of the box, brand new chuck, there's a certain amount of jaw lift that takes place. So when you clamp on a part, you clamp on a test bar, you clamp on a plug to form the jaws, you clamp on a forming spider to form the jaws, the master jaws lift at the leading edge of the master jaw towards this is the center of rotation of the chuck, but the very edge of the master jaw closest to the center line of the chuck tends to lift. And that lift changes over time. If you don't grease your chucks right, if you use inferior soft jaws and you wear the body out, the jaws will begin to lift more and more and more over time. So you have to be aware particularly when you form soft jaws, that there is a certain amount of lift in the jaws. When you form the jaws, you can, because of that lift, you can, in an effort to improve your surface contact, the gripping length, contact, the actual contact length. If you want to improve that, you can put a conical taper on the jaws as you bore them. So as you start at the face of the jaw and bore into the jaw in the z-axis, if you increase the diameter, you put a conical taper on it, and we'll say, just as kind of a thumbnail idea, is 0.6 of an inch for every inch that you bore into the jaws. So as you bore into the jaws, for every inch that you bore gripping length, if you can increase the diameter roughly 0.6, you will put a conical taper on the jaw, so when the chuck clamps and lifts, that gripping surface is parallel to the center line. So at rest, when you're not gripping apart, you're going to have a taper in it. But when it clamps and the jaws lift, it'll be straight, and you'll get more surface contact along your part length. That'll improve your gripping torque. It'll improve your ability to hold the part, particularly when you've got maybe a longer part protruding out of the jaws and you're machining quite a distance away from the face of the chuck. You want grip length. You want contact on that part. By forming your jaws with a conical taper, you can eliminate some of that lift. Again, what you're seeing here are just kind of steps with, kind of how to form the soft jaws. There are some good videos on YouTube of that as well. But these are just, I think, fairly traditional ways of forming your jaws. And of course, being the chuck builder, we get into specific dimensions and technical approach, but most people have had some pretty good experience forming jaws. The other big issue with soft jaws, and really once you bore a set of soft jaws and you dismount those soft jaws and you put them back on the chuck in the exact same master jaw location, you never reproduce the original center line, because there is a gap between the edge of the T-nut and the T-nut slot on the bottom of the soft jaw. When they're bolted down and you bore the jaws out, you create a center line for the jaws in that position at that time, at that cylinder pressure, that application criteria. Once you take them off and you put them back on the chuck, they do not repeat because of that gap. You cannot put all three jaws back on the T-nut in exactly the same position as they once were when you originally formed the jaws. Therefore, you typically have to reform the jaws. You have to cut them again when you put them back on the chuck for the same part. This is, also an area where we get calls for job repeatability and positioning accuracy. Many times it's because of this repositioning error. To do I guess kind of as we get close to the end of the presentation here, we're getting close to the end of our time together, but a little bit of a commercial, a little bit of a Kitagawa commercial here. The BR series, which some people probably heard of, the BR series is really what will be the next generation power chuck. This is the chuck that will replace the B200 and BB200 series chucks. This is a product that's been out now for just about 2 years, but this is a product that you will start to see come in on your machine tools from Japan to begin with, and then maybe some other origins around the globe. But the idea behind the BR series was really to try to address some of these common issues that we see in power chucks straight out of the box. So this isn't this is a chuck that you can buy now to replace your standard chuck, but this will become the standard chuck in the future. This chuck will become the chuck that you find on your new lathe. And the idea is that this chuck, based on its internal design, we've been able to improve jaw repeatability or clamping, your ability to clamp a part, put it on center, unclamp it, and reclamp it and put it back on center. We've essentially been able to improve that by basically by 50%. Also, we've been able to reduce the amount of jaw lift that takes place in this chuck. So right out of the box, this chuck will have a significant improvement in jaw lift. We've reduced the amount of jaw lift that takes place, in just the design of the chuck body. So some of the issues we've seen in the past with standard chucks, we've tried to reduce that in the new design. Lastly, as an aftermarket upgrade, you can also purchase what we call T-nut plus. These T-nuts, essentially, the T-nuts in the master jaws and the top jaws for the BR series are essentially designed so that they fit they fit tighter. They fit more closely together. They eliminate the gap between the edge of the T-nut and the edge of the slot on the bottom of the jaw. This allows us to form the soft jaws, take them off, and put them back on, and not have to rebore them. So it eliminates the reboring, that time where in a traditional environment you have to go find cutting tools, go find a jaw boring ring or a plug, and spend 10, 15, 20 minutes, half an hour boring your jaws again. This new chuck and T-nut plus allows you to eliminate that. And again, because this chuck will be coming on all your lathes as a standard product, it would just be adding the T-nut plus to that chuck as an aftermarket upgrade to eliminate the jaw reboring process. That's my infomercial, that's my commercial. And again, this chuck is available now. We do have it in stock. It is something you can buy and replace your standard chucks with. Of course, we will be promoting it when you call in to buy a new B208 or BB208 to replace your aging chuck. We will steer you or put you, at least give you information about the BR to give you an opportunity to upgrade now to the new technology. And then lastly, just kind of wrapping up my part of the presentation here is we talked at the beginning about some additional webinars coming down the pike. We will have a series here on right angle heads. Kitagawa North Tech recently acquired Technara, which with that we brought in angle heads. We'll be doing a presentation on angle heads. We'll do a more detailed launch of the BR series, talk about some engineered work holding solutions, repairing and rebuilding work holding. So we'll have a repair rebuild seminar. And then get into how to select the right rotary table for your application. So these are not necessarily in this order, but this is some of the content that we're going to publish and put out there and produce webinars on, coming up here in the future. So that said, that wraps up this particular webinar. As I said, we did record this. We will provide a link to the content. Info@kitagawa-usa.com is also an email that you can send specific questions to. We'd be happy to work with you and follow up on any applications that you have. And we thank you very much for attending. Have a great day.